So over here, we have the excitation, contraction, coupling. So pretty much what happens within the first step is that the action potential generated is propagated along the sarcolemma and down the T-tubules. So over here, we have the axonal terminal. And then this area over here containing the blue dots is a synaptic cleft. And then this green line, this green squiggly line, represents the ACH streaming across. So this orange tube, it represents the T-tubule, and these little white pieces of clay is portraying the bonds that bind the SR and the T-tubule together. And then within the SR contains calcium. So the calcium flows along and reaches the trypomyosin, or the, this black part, this black band represents the trypomyosin, and this white dot over here represents the tryponin. And then the straw is what portrays the actin. And then this, then over here we have the myosin cross bridges. So pretty much in the second step, what is happening is that the action potential that triggers the calcium and releases from the terminal of the SR. So pretty much it's just releasing, the action is releasing the calcium to let it go to the actin. And then over here we have the myosin and the myosin end, and then the calcium ions they bind to the tryponin. So pretty much they touch the tryponin, and the tryponin changes the shape, removing the blocking action of trypomyosin actin active sites exposed.
Okay, so right here we have the myosin, and it attaches to the actin and then detaches, pulling the actin filaments toward the center of the sarcomere, and it releases the energy of ATP. So then the calcium will travel back to the SR, the active transport, and then we go to the tropomyosin, and it's restored the actin active site right here, and this is how the contraction ends and the muscle fiber relaxes.
Okay, so now talking about the sliding filament theory, we're going to go through some of the steps and just how this works. So first, it starts with a nervous impulse. It allows the chemical to release acetylcholine, and it causes the depolarization of the motor end plate. Now, what exactly is the motor end plate? Well, it's pretty much a motor neuron establishing a synaptic cell connection with the striated muscle cell. And this change in polarity allows calcium to be released from the sarcoplasmic reticulum. So now let's go into the next step. The calcium binds to troponin, and it deforms its shape and moves troponin from the active site of the actin. Next, the myosin filaments can attach to actin, forming a sort of cross bridge in a sense. And so the breakdown of ATP releases this burst of energy, allowing myosin to pull actin filaments closer together, which allows the muscle to contract and shorten. And so when the myosin attaches from the actin, the cross bridge is broken down, and the ATP binds to the myosin head. And when the ATP is broken down, the myosin head can again attach to the actin binding site. This furthers along the actin filament and repeating this this stroke of power. And so lastly, once this impulse of contraction stops, the calcium is pumped back into the sarcoplasmic reticulum, and now the actin returns to its resting position. Thus, the muscle is now lengthened and relaxed.
Looking at the diagram to the left, it shows a stretched muscle where the I bands and H zone is elongated due to reduced overlapping of the myosin and actin filaments. There would be reduced muscle strength because few cross bridges can form between the actin and myosin. As the diagram to the right, you can see that is a fully contracted muscle with lots of overlap between the actin and myosin. Because the thin actin filaments have overlapped, there is a reduced potential for cross bridges to form again. Therefore, there will be low force production from the muscle.
Go away, actin! Oh no, the bridge is broken!